All right, welcome. It's a little bit dark in here, so let me just adjust the light a little bit. Okay, here we go. So like we said, we usually assume that we carry out repeated experiments to get a sample, what is known as samples. I hope you can hear me now well. I mean, this new microphone is here, so a very common way is to discuss the frequency distributions and so forth. I'm not going to go in depth here, but two really important concepts that we discussed were sample variance and sample mean. So these are the things that we gather when we sample, and by sample we mean n, some number of experiments that we assume are independent from the distribution that we are trying to study or examine. And we'll skip the relative frequencies. We talked about this a little bit. I showed you how to calculate the mean and the variance using MATLAB and so forth. We will not be drawing histograms on this course, but you know, you can do this fairly simply. All right. Also, we talked about, sorry, the dust. I took a coronavirus test and it was negative, but the dust outside seems to be causing some. So we talked about the Bernoulli distribution, which is basically a weighted coin toss. So it's something that either happens or doesn't. Usually we mark it as a random variable that gets the value 0 or 1, and 1 happens with probability p. So it has only one parameter. That's the probability of the success, which is number 1 happening. We talked about the repeated Bernoulli experiment when we repeat it n times. This is known as the binomial distribution. And when we repeat the Bernoulli experiment n times, we get a discrete sample space. We calculate the number of successes, and we get a discrete sample space that consists of the numbers between 0 and n. And the probabilities we also discussed. This is the density function of the binomial distribution with n repetitions and probability p. We had this definition, and the binomial formula gives us the way of calculating the expected value. Variance was calculated using the moment generating function. We can skip that. You can just remember that the variance is gained by taking np times p minus 1. And we see here that the variance is basically minimized when p is close to 0 or close to 1. So if p is very close to 1, then p minus 1 is very close to 0. If p is close to 0, well, p is close to 0, and this variance is small. And it obtains its maximum when p and p minus 1 are both 0.5, in which case the variance is exactly n divided by 4, really. So here we have a regular coin, which is sorry, tossed n times, and that is the simplest, basically the simplest binomial distribution because it's symmetric. There, the probability is 0.5. We talked about this manufacturer transistors example. We calculated this using MATLAB. Here are the commands that you can use. All right. So binomial distribution is something that you should be familiar with from previous courses, but it's really important, and it's really important to understand that the expected value is very simply n times p, and the variance is n times p minus 1. We will be needing these properties here. So another important distribution, in addition to the binomial distribution, is the so-called Poisson distribution. And now in this case, we'll describe shortly the sort of processes that give rise to the Poisson distribution. But we can think of it as a possibly infinite sample space, consists of non-negative integers 0 to some number. I mean, it goes all the way to infinity. And we say that it follows the Poisson distribution with this parameter lambda. And it's just one parameter, lambda. And it has this density function that looks kind of like an exponential function, but really, I mean, the k there only appears in the exponent lambda to the k divided by k factorial times e to the minus lambda. So the thing about this Poisson distribution is that it's used, and I'll explain shortly how and why, it's used usually, or happens, or it's a model of the sort of situation where something may happen basically any number of times, but there's an average time, it's known on average how many times it happens in a certain time interval. And that's actually our parameter lambda. And then we measure it for a certain that amount of time, and then we count how many times that thing happens. So there are several examples we'll see of this situation, and we'll see also a mathematical justification. We can ground this model, or we can justify this model based on the binomial distribution and ultimately the Bernoulli distribution, but we'll get there shortly. Here are some examples. Here's Poisson distribution with parameter 1. It's looks like that, and Poisson distribution with parameter 3, it looks like that. And when the parameter becomes bigger, this tail becomes longer, and the top of this tail basically, or the top of this this bump is roughly around the parameter value lambda. The thing about the Poisson distribution is, well, you can skip the fact that it has this moment generating function. We can calculate its derivative and so forth. We'll skip that for now. The thing is that it has the parameter lambda, and lambda will be its expected value and also its variance. So this means that when lambda is very, very small, it also has a small variance. So when lambda becomes small, this becomes the kind of a distribution that is very close to zero. I mean, it's almost all almost all the probability mass is around zero, and then it's very steeply decreases when lambda becomes close to zero. On the other hand, when lambda becomes very large, also the variance is relatively large, so it becomes the bump is more attenuated, you know, the higher the value of the lambda is. The thing about Poisson distributions, we'll come up with this model, is how we arrive at Poisson distribution is that they approximate binomial distributions for very large n. You can think of it this way. We have a binomial distribution. This is what we could call a coarse approximation of something. So we think of some process as, okay, someone is tossing a coin n times, and it has a probability p of landing heads, let's say, or we're carrying out n Bernoulli experiment with probability p. The crucial feature of this binomial distribution is that it's very coarse. I mean, when n is small, yes, it has an expected value n times p. But the idea is that this is the expected value is known, and we model this as repeated attempts at let's say blinking some light. We have a button, and that's a certain probability of a light blinking, right? And we don't know necessarily the probability, but we say that, you know, it has a tendency to blink. And if we press it repeatedly, we repeat this experiment, but let's say that the expected value of the light blinking doesn't really change. I mean, if we have a fixed time interval, it has a tendency to blink, let's say 5 times in 10 seconds. So within 10 seconds, if we press this 10 times, once every second, we have an expected value of 5 successes. But it's not increased. If we press it 100 times, then the probability that it blinks at each button press becomes smaller and smaller. The expected number of blinks in that 10 second remains fixed. So the idea here is that when n goes to infinity, then the probability distribution of this light blinking with how many times it blinks in 10 seconds is going to follow the binomial, the Poisson distribution. So the idea is that we assume that n times p, the expected number of successes, is fixed. But as n grows large, we also let p go towards 0, all the while in such a way that n times p is maintained as at fixed equal to lambda. So we look at the density function of this binomial distribution at a given value of n. Now remember, lambda is fixed, and if n increases, then p is lambda over n. So at each value n, the density function is at point k is n choose k times lambda over n to the power of k times 1 minus lambda over n to the n minus k. The thing about this is that we can now write open this n choose k as a factorial thing. Also, we write open this lambda over n to the k at lambda k divided by n to the k. And then we have 1 minus lambda over n to the power of n. And then we separate this 1 minus lambda over n to the n minus k as a product of lambda 1 minus lambda over n to the n. So what we have here, let me just show. So this term here becomes these two terms here. We are separating that into two. Can you see my annotation? Is it visible?
Yes.
Okay, good. And this n choose k becomes that, and this becomes that over there, right? Now, we can rewrite this so that we divide this each and every term here and we then take this and combine that with this to get this term here. And then this product, we just rewrite it as that when we are dividing it with n to the power of k. You can prove that that's actually what happens there. Now, the last two terms remain the same. So when we let n grow to infinity, then 1 over n goes to 0, as does k minus 1 over n. All of these go to 0 as n grows to infinity. So let me just clear this. So let me just explain what is happening here. There are k terms. Oh, wrong color. I'm doing it here. This blue box here, I'm going to do a blue box here. So this blue box here, this is a product that contains k terms. We take this n to the power of k and divide each of these terms with n. And take the product there, right? Separately. So what happens is that we get these terms here. Each of them approaches 1 as n approaches infinity. So we are left with these terms here as n goes to infinity. So what happens to them this, and I'm going to use another color, the red box that I'm going. So we know that this approaches the e to the power of minus lambda. And then this term, as n grows to infinity, remember k and lambda are fixed. So this term here approaches just 1. So what we really have is only this blue box and this other red box here. So we are left with the density function of lambda to the k over k factorial times e to the minus lambda. That is actually the density function of the Poisson distribution. The idea is that when if you consider a binomial distribution with a very, very large n and very, very small p, and we have we can think of it that there's a very rare event in a very, very long sequence of things happening. So then we can approximate if n is very large and p is very small, then the binomial distribution with parameters n and p can be approximated with the Poisson distribution n times p. This is actually what we are going to be doing. Think about it this way. I don't know if you know how radioactive decay works, but in essence, radioactive decay works in a way that if we observe a relatively stable element, let's say radium, it's radioactive, but it's relatively even better. Let's observe uranium, one of the more stable isotopes of uranium. It has a very, very long half-life, like in the order of, I don't know, let's take plutonium, it's better. Plutonium with millions of years for half-life, or maybe depending on isotopes, some have millions of years of half-life, some have hundreds of thousands of years. So the probability of a single atom, spontaneously decaying, so it releases a neutron or releases a beta particle or alpha particle or something. In any case, exhibiting radioactive decay, a single atom within 100 years, 100,000 years, let's say that's the half-life. It has the probability of 1/2, so it's a 0.5 or 50-50 chance of decaying when we observe it for 100,000 years. So if we observe it for 1 day, then that is going to be a very, very small p, very small indeed. I mean, there are 365 days in a year, so if it has 100,000 year half-life, then we can roughly, and this could be roughly, say that it has a probability of 1 in 73 million or something like this chance of decaying today. That's a very small number. However, if we have a big chunk, like a fistful of that material, that's plutonium, uranium, something like this, then that has a huge and enormous number of atoms in it. So here, n is very, 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 very large. So we will be observing probably millions of decay events during a day for a very, very minuscule amount of this, this radioactive material. And we can model this, this distribution of these radioactive decays as a Poisson distribution. Here's an example, another example. Let's say that out of 100 signals sent, on average, we have 1 signal that suffers from a transmission error. So let's say we are sending a beep, 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 something message like this. So it has a 100% chance of being a boop instead of a beep. So this is just a We send 200 independent signals. The probability that at least 3 signals suffer from errors is needed. We need to figure out what is the probability that 3 errors occur. So we can model this firstly as a binomial distribution. So we have 200 repetitions, each repetition having a 0.01 probability of creating an error. We can approximate this, not approximate, but approximate only in the sense that we are not using full symbolic here, where we're approximating in the sense that we're calculating with floating point numbers. So we can calculate this from the binomial distribution. We calculate the probability that it's 1 minus 0 events, 1 events, 2 events. We get about 32.33% chance of having at least 3 errors in these 200 signals. Now, alternatively, because we have a very large, well, it's debatable compared to a radioactive decays, but we have a large-ish n, 200, a small-ish probability, 0.01. Their product is 2. So we can approximate this with Poisson distribution with lambda equal 2. And what we get is very, very closely the same probability, 0.3233. So the Poisson distribution in this case is a pretty good approximation of the binomial distribution. So my point here, I'm trying to make with this is not that, use binomial distribution and then approximate with Poisson distribution. It's just to give you a philosophical idea of what I'm going to just shortly explain to you, what is called the Poisson process. And we tend to use the Poisson distribution as a model of randomness when we have what is called the Poisson process. We call a process which spews out randomness somehow, some process that follows some kind of random pattern. We call it a stochastic process. There are several of these. The aforementioned radioactive decay, number of radioactive decays or radioactive decay or some kind of radioactive decay events emanating from a sample of radioactive material can be thought of as Poisson process. There are others. Very often it's used as a model for traffic accidents, infections, when traffic accidents or certain illnesses or diseases occurring in the general population, not transmissible diseases, by the way, not that kind of, but something like heart attacks that occur in certain area or something like this within a time interval. And a process is known as a Poisson, well, it's modeled as a Poisson process if it satisfies these following assumptions. So whenever we look at time intervals, someone has a mic on now? You have a question? I'm not seeing who has the mic on there. There's a, I think Q, you have your microphone on. I think if it's not deliberate. Let me just, okay, thanks. Yeah, I mean, if you have questions, feel free to ask questions. I'm just talking here, but we'll shortly get to some exercises. So if we have non-interlapping time intervals, so let's assume that we have this radioactive material that doesn't have a very short half-life. It doesn't work if it has a very short half-life because most of it will be gone tomorrow. But if it has a very long half-life, like let's say uranium that has hundreds of, I think uranium-235 has something like in the order of 100,000 years or something. I think that's the decay, right? So if we're talking about days, not eons, then if we have today or tomorrow or next Tuesday is the time interval, and they don't occur, then the number of radioactive decays within those time intervals is independent. Or if we're talking about heart attacks, so the number of heart attacks occurring today as opposed to next Friday are independent. You know, so the hospital can think that, okay, the number of heart attacks is a Poisson process, and the amount of, then they prepare for the contingency of how many heart attacks, you know, happen, and they have some devices for treating those. They may not be independent in this scenario, by the way, because we have the Easter holidays coming, and in some parts of Finland, people tend to overeat during the Easter holidays, so you may get more heart attacks. I'm not sure if that works like that, but I'm just guessing. The idea here is that in the long run, the number of times that A occurs within 1 unit of measurement, and we don't know what measurement. This could be also either distance. Usually we think of time, but it could be a distance as well. For instance, if we are driving a car, a motor car, then usually we model the number of, a car manufacturer has to replace certain components when a car has warranty. Let's say a car has a 7-year warranty, and then they have some model, they probably model it as a Poisson process, you know, the number of breakages or the number of components that you need to replace within a time unit. But it's not necessarily time, it could be kilometers. Like for a car, you have something like, usually when cars are maintained, then certain parts are replaced based on how many kilometers you've driven, the distance, right? So you have a number of times some component breaks. Depends on how far you drive. So the unit may be kilometers or hundreds of kilometers or thousands of kilometers. It may be time, like years, days, weeks, depending on what you're measuring. The long run meaning here that if you're looking at if you're taking several days, if your unit is day and you're looking at hundreds of days, then you have some probability Q that it occurs in each day. Where this is a small, I mean, let's say we're talking about years, you know, if we're talking about years and the unit is days, then we have a probability of something occurring today, something occurring tomorrow. The probability that this event happens if we take a very short look and it happens more than once, is very low, approximately 0. So they don't, the occurrences do not tend to cluster. So this rules out situations where you have a random event triggering immediately with relatively no delay, or a delay very small compared to the average time span it takes for these things to happen. There's no triggering effect, so that they happen in pairs, for instance, these events. In radioactive decay, for instance, this rules out the situation where we are at or close to being a critical mass, right? So if we have a radioactive material that is close to being critical mass, then the model for modeling the radioactive decays is a Poisson process may not be appropriate, because there's some chain reactions going on, something like this. With these assumptions, we can demonstrate, and I'm not going to demonstrate it here, but if these 3 assumptions occur, or you know, these 3 assumptions are in place, or they're reasonable, we can model the process as having a Poisson distribution, so that if we measure time between two intervals, T1 and T2, it could also be distance. Then we have lambda equals this Q, which is the time unit probability times the time interval's length. And the number of times it's going to occur is Poisson distributed. So if a heart attack appears in a small town, once a week on average, then if we think about the yearly number of heart attacks, it's pretty well Poisson distributed with lambda equal to 52. Here's another example. 1 gram of radium isotope 226 emits on average 3.57 times 10 to the power of 10 alpha particles per second. So you see, I was talking about, this is very, very big number. Compute the probability that within 1 nanosecond, so that's 10 to the minus 9 seconds, that it emits exactly 35 alpha particles, and the probability that it emits 27, 28, or 29 alpha particles. We model this as a Poisson process. We can take this time interval to be a nanosecond. And we know that that's 10 to the minus 9 seconds. So we can multiply this average by this 10 to the minus 9. We get 35.7. That's the expected number of alpha particles within 1 nanosecond. And we can take the Poisson distribution. We can calculate the probability that X is equal to 35, and it turns out it's 6%. So it's actually not a ridiculously small percentage. The probability that it's between 27 and 29, you can add this probability that it's 27, 28, and 29. Those are disjoint situations. And you get a 9% chance. Like I said before, the interval in question doesn't need to be time. It can be length, area, volume, any such activity. For instance, rainfall. You can say that there's a certain, usually it's given as millimeters, rainfall in millimeters. That means that regardless of how big or small a container you place, a certain amount of water comes in there, it fills it to some amount of millimeters. But if it's if the big drops and it's not very heavy rain and it doesn't last very long, then you may have a very small container and you capture the raindrops. So you may have several containers and it may be Poisson distributed depending on how many raindrops fall in a certain area. This MATLAB has these commands. We have the Poisson, so it's written like this, POISS, short for Poisson. PDF, probability density function, that gives you the probability at a given point. And CDF, the cumulative distribution function. The question before is now, why does this second one work? Why do we get the same result? All right. Let's have a 10-minute break now. We'll continue at, okay, we're back online. And if you have any questions, you can interrupt me at any time. We'll have a short break also before the end, shortly. Here's another example. Assume that this random event occurs X times in the interval 0 to T, so that this X has the distribution, Poisson distribution, lambda T. So lambda T means, lambda is when T is 1, then this is sorry, when T is 1, then this event occurs X times and X follows the Poisson distribution with lambda. But when we take another T, an interval from 0 to T, then it's t times lambda, obviously. Now let's see that, let's define t, capital T, as the time at which the first event occurs. In particular, if no events occur in this time window, we get the probability e to the minus lambda t, so that the probability that the first event occurs within this time window, so that it has at least one event in this time window, so between 0 and t, small t, then the probability is 1 minus e to the minus lambda t. Now recall, the probability that this time is smaller than t, this is clearly this one here. Let me just annotate this a little bit. So this here is clear. It's clear we have a probability that something is smaller than this t. Here's the function that describes that probability. This is a cumulative distribution function. This is the cumulative distribution function of something. And this is the cumulative distribution function of you know, something not, or something occurring at least once before some given time, right? And if we define the function g as the derivative of this function, we get lambda times e to the minus lambda t. So this is a density function of a so-called exponential distribution. And what does it mean? It gives, you know, it gives the distribution of the time between two different events. If we measure, if our random experiment, if we have a Poisson distribution with parameter equal to lambda, lambda being the number of events in one time unit or one distance unit or whatever, then the distance between two events that is also a random process. So take an example, we have a very minuscule amount of some radioactive material, a very minuscule amount, small enough that it's that the number of radioactive events is very small within, let's say, whatever time we are measuring it, but big enough so that there are still many of these atoms left after a few of these decays, so that it doesn't really matter. A very small proportion of these atoms are decaying within the time frame that we are actually interested in. The density function, alternatively, you can think of, let's say, we have a Poisson distribution that describes how many car crashes occur, let's say, within 1 week inside one city. In this city, let's say there are an average of 20 car accidents per week. And we can derive the density function for the random process, which is the time between two accidents. So let's say we have about 20, car crashes per week, or 3 per day, roughly. So this way, if we had lambda equal to 3, let's say, in our Poisson distribution, then if we're measuring days, the unit is days, and lambda is equal to 3, then we could define a continuous random variable, which is which we can get by measuring the time between two car crashes. And it would have this 3 times e to the minus 3 times t, where t is in days. We get the density function for the random variable that measures the number of days between two car crashes. We could shorten this into hours, in which case lambda would be some relatively small number here. I think about 3 divided by 24, right? So the exponential distribution and the Poisson process have a very, very strong connection in this way. So if you have a Poisson distribution for a number of events in a time frame, then you're going to have an exponential distribution for the time between two events. And those two come in pairs. So alternatively, if you have a situation where you have an event and you have an exponentially distributed time between events, then the resulting situation is a Poisson distribution. So coming back to the material that we already discussed, we said that it's very common for us to measure model, let's say, occurrences of some maintenance requiring events, such as component breakage or something like this. The time it takes for some component to break, for instance, we measure it as an exponential distribution. So when we have a number of those components, of course the distribution is different, then the number of breakages, the number of times it needs to be replaced, the component needs to be replaced, is Poisson distributed if we have an exponential distribution for the time it takes for the component to break. So every time it breaks, we replace it with a new one. The new one now has an exponential distribution, and then we wait until it breaks and so forth. So if we take this process and we look at it for over a relatively long time, then the number of components we will be needing within that time frame will have the Poisson distribution. So these two distributions are very, very closely linked. Sorry, the annotation tool was on, so I couldn't change the page. Now we'll talk about what is arguably the most important distribution in all these continuous distributions, and we call it the normal distribution. The normal distribution has two parameters, mu and sigma squared. Basically, it's fully characterized when we know three things. It's a normal distribution, and we know its expected value, and we know its variance. You don't really have to learn this density function, but it helps. It helps to understand how this density function works. And the thing about this distribution is that normal distributions have basically the same shape. Of course, they may be flatter or wider, but if you just zoom in or zoom out, then they actually can be made to look exactly the same by just shifting and scaling. So, you know, usually it looks something like this. The density functions curve. Again, I'm terribly sorry for my lack of drawing skills. So the density function curve looks something like this. And this is mu, and this may not be in exactly the right place, but we have a situation like this. When we zoom so that this mu is at the center and this mu plus sigma and mu minus sigma are at the same places, are at this distance, then all the curves will have the same shape. You know, it may be scaled bigger, smaller, but if we change the scale so that the sigma is there and translate so that the mu is there, then they will always have this similar shape. Of course, it's not exactly equal. It's not completely trivial to show that when we take this density function as a density function, then its integral over the real numbers is 1, but it can be done using theory of integrals. I'm not going to go there. It's completely symmetric around mu. The history or the rationale for normal distributions is mathematical, and we will explain it shortly how it works. I'm not going to go through this proof, but it will be proven in, it can be proven, and the proof goes under the name of central limit theorem. And it's very important to understand what the central limit theorem says. We'll discuss this later a little bit. But the idea of normal distribution is that many natural phenomena tend to follow the normal distribution. There is this theory for the moment generating function and expected value. The important thing is to understand is it has an expected value of mu and variance of sigma squared, and the density function is expressed by this rather canonical or rather common function. You should probably remember this. I'm not going to ask you it, but you know, you can always look it up in a table. But really, I mean, I think it's like common courtesy or something like being moderately civilized in mathematics or moderately educated in mathematics is you should know the density function of the normal distribution, what it looks like. You know, just remember the formula. Not going to go into this all this proofs with the moment generating function. There's a parenthesis missing over there. There should be close parentheses. You can calculate this and it can be done with not very hard algebraic manipulation of there, but you can verify that this is in fact what it boils down to. Some important theorems here that can be proven from the definition is that if we have a normal distribution and we employ any linear transformation on it, then the resulting distribution will also be normal distribution. And this cannot be stressed enough, that this is a highly important reason why normal distributions are used. So if you have a normal distribution and you impose a linear transformation on it, subtract something from that, multiply it with something, the resulting variable after this transformation will have a normal distribution. And in particular, if we can normalize, and this is the reason why we use normal distribution. Well, this is the reason why normal distributions are so easy to use, is that if we have an expected value and variance of some normally distributed variable, then we can normalize it into a random variable that follows the normal distribution with exactly 0 expected value and variance of 1. And this is done by first subtracting the expected value and then dividing by the standard deviation or the square root of the variance. And what we get with this is the so-called N01 distribution. And this N01 distribution is the one that we operate with mostly. The reason is that linear transformation, or actually affine transformations, in this case, y equal to ax plus b, and if we choose this as in such a way that it's actually x minus mu divided by sigma, then we get the N01 distribution. Or, you know, a is 1 over sigma and b is mu minus mu over sigma. Then we get the N01 distribution. And we use the same symbol of this theta z for the cumulative distribution function. And this cumulative distribution function is often pre-calculated in tables and you know, given as a, in basically all statistics books will have this cumulative distribution functions table given at the appendix or at the end of the book. We cannot express the cumulative distribution function as using elementary functions without integrals. So it needs to be computed numerically, and historically it has been computed already in huge tables, which we can read. I'll show you an example of it. Just a second. I'll show you an example of such a table. You can find it in Moodle, here. Here's an example. Let me just share it. Here's one example of such a table. So very often we have this Z score. I mean, we are looking at the value of the Z, and we are looking at this cumulative distributions function. So the way we calculate this is that if we want to look at the probability that our N01 distributed variable Z has a value smaller than or equal to 2.5, and we look at here 2.0, sorry, 2.5 and 0.0, so it's here. So N01 has about 0.63% chance of having a value greater than 2.5. Alternatively, it has a 99.379% of being smaller than or equal to 2.5. So, of course, these are the negative values are, you know, exceedingly rare. Right. Let me get back to the material. So that's why we often, I mean, they're very common, the use of these tables. Sorry, I'll have to resume that share. It can be found here. Right. Now, old school way is looking up that table. You don't have to, but if you are more familiar with looking at these lookup tables, then just go ahead. You can use software as well. In MATLAB, for instance, this theta will be expressed by the MATLAB function called normCDF. So let's do the following one. Let's say that we have this we model adult female height in Finland, and I'm not sure if these numbers are correct. I picked these up from some examples, so the numbers in this may not be completely accurate at this time. But the average female adult is about 165 centimeters tall, with a variance of 6.5 to the power of 2, meaning 6.5 standard deviation. So it's got mu is 165 and sigma is 6.5. So we generate this random variable Z. We often mark this N01 variable as Z. If the normalized variable is often denoted with Z. So we subtract the mu 165 divide by sigma, divide by 6.5. And the probability that we want to calculate the probability that a female random person will be registered as having a height of 165 centimeters within 1 centimeter accuracy. So it's really that the probability that their true height is between 164.5 and 165.5. So we normalize both X and these values. So from both of these values, we subtract 165, and both of these values we divide by 6.5, and then this normalized variable z will be the probability that this x is between these two numbers, 164.5 and 165.5, is in fact equal to the normalized variable z being between minus 0.08 and 0.08. We can calculate this from the lookup table, calculate this by finding this 0.08, or we can use MATLAB to do this. We'll do this later. You can use the norm CDF to calculate this. So you could, it's just norm CDF 0.08 minus norm CDF minus 0.08. So they have about 6% chance of being average. So most people will be taller or shorter. The probability that they're between 154 and 175 is in fact far higher than, it's about 90% or 89.5% chance that they are within about 11 centimeters range around the average height. We can compute the height. Also, we can do this in an inverse manner. So we want to calculate what is the threshold for being at 1% tall, top 1% of tallest women. So the way we do this is we first calculate the threshold for 0.99. And in the normalized N0 distribution, we can find it in the table at 2.33. I'll show you shortly how that is. You can find this with the norm inverse of the norm CDF. It can be found also in MATLAB, this inverse of the norm CDF. We'll learn this in the exercises. So you take this number, take the inverse of this CDF, you get 0.99. Sorry, take the inverse of this, inverse of this cumulative distribution and take it from 0.99, you get 2.33. Then you can go back. Look, the normalized variable is x minus 165 divided by 6.5. So in order to get the actual value c, you get c minus 165 over 6.5, solve for c. So you get 180.1 centimeter. So to get to be at the top 1% of tallest women, you'd have to be above 180.1 centimeters. We'll revisit this normal distribution in later examples. I mean, it will be the go-to distribution when we model statistics. There are some caveats that need to be dealt with, but we'll deal with them later. Let's now discuss ways in which the normal distribution appears. Among others, remember that when we had a binomial distribution where n times b, was constant and n increases, we have a fixed expected value for a binomial distribution, but n becomes large and p becomes small. Then we get the Poisson distribution. On the other hand, if both n and p are very large, and p is very close to being 0, if n is very large and p is very close to being, that's actually not very large, but if n is large and p is very close to being 0.5, then the normal distribution with expected value, well, comes from the binomial distribution n times p, and variance n times p times 1 minus p is a good approximation for large n. So the binomial distribution will look like a much shifted distribution, normal distribution. Well, what can we do is we can use, what is this good for? Well, this is good for when n is large, we can actually just use the normal distribution and not have to worry about the highly combinatorial calculations of the binomial distribution. So we don't have to calculate these n choose k's and so forth. So we can instead use the normal distribution and get a pretty good approximation. Here are the MATLAB codes. So norm CDF is in fact this cumulative distribution function, that theta that we were talking about in these examples. This is given us how we can calculate it. The norm CDF also takes the, if you don't give it any parameters here, it assumes it's the 0, 1, but if you give it the expected value and here you don't use variance, instead you use the standard deviation, then you get the you can get the results directly. And also the inverse, the norm inverse, oh, there's an error here. That should be not 65, that should be 6.5. There's a typo there. All right, let's have a small break now, whereby let's go back online. So that's our first brush with the normal distribution. The last thing about today, we'll discuss a little bit about samples. I mentioned earlier the sample variance and sample deviation. So now in this section, we will discuss the sample distribution, meaning that when we take the sample and we calculate the average, or we calculate the sample mean and we calculate the sample variance, then that in itself is also a random variable. And when we know the original distribution, then that random variable, adding those two things together, will follow some distribution, and we look at what happens to that distribution. What does it actually do? This can be then, this theory can then be used to justify things like, you know, we estimate what is the variance of the original distribution, or we estimate what the expected value of the original distribution from which they are, these random samples are from. How does it look like? Also, we can use this theory to justify why we actually use the normal distribution, because these distributions tend to follow, the sample distributions tend to follow normal distributions. That's a little bit dangerous because then people tend to assume all distributions are normal distributions, and that's definitely not true. So without further ado, let's get to this material. I'll use a few minutes to talk about this, and we'll stop in about 10 minutes yeah. So it's important to understand these independent random variables that have the same distribution. So these are random variables in and of themselves. So up to this point, we've said that, okay, you are rolling a dice, rolling the dice or rolling a die, and that die, or this, you know, you bring this to you bring your hand like this, and here is the die, you're going to roll it. This is your random variable, and then what comes out is the value of that random variable. And we can do it again, and we kind of thought it's the same random variable. But really, honestly, it doesn't really matter. We can think of each separate roll of the die as a separate, different random variable. The only thing that, because we're using the same die, they have the same distribution, but they're not the same variable. I mean, it's roll number 2, roll number 3, roll number 5. Similarly, but not quite as justified way, we can carry out any random sampling, any random variable we have, or random process or random model. We carry out the random experiment n times, and we assume that we get n different random variables and the results are independent. This may or may not be true, the independence, or, well, it's not true ever, but it may or may not be an appropriate model or accurate model. When I say it's never true, I mean, let's say you are sampling by picking up people from the street, then usually this is definitely not independent in the sense that they perhaps live in the same city and so forth. These people interact with one another, so they're not really independent. But it may still be an appropriate model in the sense that there is no obvious or systematic way in which this sample points depend on one another. Let's first look at the situation where we carry out an experiment n times, and then we just add those variables together. So think of this as, let's say we have a die and we're rolling it 5 times and we're adding those numbers together, the die rolls together. Or we're taking n people and we're adding their height together. Obviously that addition can be done, although it's probably meaningless. We can prove the following, which is not too hard, by use of the moment generating functions. I'm not going, like I said, I don't expect you guys to learn how to use these moment generating functions, but I'm just giving you glimpses of how they can be used to prove very, very nice theorems. So if we have independent random variables, x1 and x2, then we can actually formulate the moment generating function of y, which is equal to x1 plus x2, by simply multiplying the moment generating functions of x1 and x2. Because they're independent, then any functions thereof are independent. So this e to the t x1 and e to the t x2 are independent, and because the moment generating of y is the expected value of e to the ty, we can express this as eventually as the sum of e to the tx1, the product of e to the tx1 and e to the tx2, and those two variables or those two functions being independent gives us that this is the product of the moment generating functions. Again, not necessary to go in depth here, but these sort of techniques then be used to prove several very, very important and interesting theorems. In particular, for binomial distributions, if we have two independent binomial distributions, we take a sample from one and sample from the other, we actually get that their sum is also binomially distributed. If they have the same probability, success probability, P, then the sum of these two variables is also binomially distributed variable with the number of experiments is equal to n plus m. It's not surprising if you think about it, really. It's not true if the two p's are not equal, if the probabilities are not equal. A really important corollary to this is that if we have n normally distributed variables, each having their own expected values and variances, and they're independent, meaning that there's no covariances there, then the variable that is a linear combination of these is still a normally distributed variable. And if it's a linear combination, then the expected value of this y is an analogous linear combination of the expected values of these component variables, and the quadratic linear combination of the variances is the new variance. The proof is rather straightforward if we apply the moment generating function. Not going to go there and not expecting you guys to do this. I just want you to be aware of the sort of techniques that can be used to prove very difficult properties of these distributions. Now, if we consider a random variable x, which we take an independent random experiment from. So every single occurrence xi of this random experiment is independent of all the others, and it has the same expected value and variance as x. So in this case, we call this sequence of this sequence or this sample. Sorry, we call this sequence of variables. So first attempt, second attempt, and nth attempt or experiment. We call this sequence as the sample of x. So we think that there is like this one random variable, and then we're generating n experiments of the same variable. Then this sequence of n experiments, the result is a random vector basically, which we call the sample of x. Each component has the same expected value as x, and each component has the same variance. And statistics is basically the study of such samples. And what do they mean? So we call these numbers that we calculate, these descriptive numbers that we calculate by use of the sample, we call them statistics. So, first order, the sample mean is defined as simply the arithmetic average of these random variables. The sample mean in itself is also a random variable, not to be confused with the particular value that this sample mean gets. So there's the random variable, which is sample mean, and we can take let's say we are dealing with a sample size 10. We can take one sample, we can take another sample, we can take a third sample, and so forth. In all of these, we are dealing with the same random variable, but it's going to have different values. If we take 10 persons and measure their height, 10 persons on the street at random today and measure their height average. We take 10 persons on the street tomorrow, measure their height average, and so forth. In different days, we're going to get different results for the average height. So the sample mean can be thought of as a random variable itself. And the actual realized value of the mean is, with this lowercase letters, is what the value that we get when we actually measure them. Usually when we have data, then we have just these measurements. Of course, we don't know, we cannot be sure what the actual random variables are. It's really important to distinguish between the actual realized mean and then the sample mean as a random variable that could be something else. If we have the expected value at mu of the original variable and variance at sigma squared, then the random sample, when we have the random sample, then the random sample's sample variance has, the sample mean has the same expected value as the original, but its variance is smaller. It's sigma squared over n. What is the variance of the mean, sample mean? Well, we can calculate the linear combination of variance, right? We add this variance n times to itself. So it's n times sigma squared, but then, each one of these variables is multiplied by 1 over n. So it comes out of this computation as 1 over n squared. Remember, it's this quadratic linear combination. So what remains is sigma squared over n. And it makes sense. It makes sense. If you calculate the average of a sample, then it's going to be pretty close to the expected value. On the other hand, the variance in this becomes smaller and smaller the bigger the sample is. If you have a huge sample, then if we take, let's say we take 100 samples instead of 10. Then if we take 100 samples today, 100 samples tomorrow, and 100 samples the day after that, each of these samples, they will look more alike than those samples in which we took just 10 today, 10 tomorrow, 10 the following day. They vary less. This is basically this, the second part of theorem 5.4 is the reason why we tend to trust statistics when we take large samples. This trust may or may not be misplaced, but here we have it. This is a highly, highly important theorem here. All right, we'll stop at this and we'll continue our discussion actually not next Monday, but the Monday, not Thursday, because there's the break because of the Easter holidays, and not next Monday because that's still an Easter holiday. So it will be a Thursday of the following week. By that time, I hope to have cleaned and made those a little bit nicer, all those videos that I'm going to be sharing. So I'm now going to stop this recording. If you have questions, you can ask me.